Lecture number 2. It's entitled Direction of International Earth Science Programs. Our speaker tonight is Dr. Michael Freilich. Dr. Freilich has been the director for NASA's Earth Science Division since November 2006. He came to NASA from Oregon State University, where he is full professor and associate dean in the College of Oceanic and Atmospheric Sciences, and he was the principal investigator for NASA's Quick Scatterometer mission. He directs all of NASA's flight, research, applied sciences, and technology development activities relating to Earth observation. Dr. Freilich presided over the recent large increase in NASA funding of Earth science and led the development of NASA's Climate Architecture Plan. In November 2011, coming up in just a few months, he will become the chair of the Committee on Earth Observing Satellite Strategic Implementation Team, COSIT. So without further ado, allow me to introduce to you Dr. Freilich.
Thanks, Jim. Thank you very much, and thanks to all of you who came here on this incredibly beautiful day. And I do realize that I'm standing between you and dinner or evening entertainment. So hopefully I won't drone on too long. Today, and by the way, right from the start, let me say that this image that's shown here is, in fact, a composite from international missions. It's land color from the MODIS instruments on NASA's Terra and Aqua spacecraft, but in the tropical regions, overlaid is color-coded Japanese L-band pulsar data. And what I want to talk to you about today is, in fact, international cooperation in Earth-observing missions. So there will be some science in this talk, there will be some results in this talk, but actually there's going to be a fair amount of discussion of the intersection of technology and maybe sociology or governance. For those who need to leave early or who regret their decision to come in the first place, I'll give you the outline of the talk right from the start. Satellites provide us with a unique view of the global system, and I'll be showing several examples and results, certainly not comprehensively, of that. The satellite measurements coupled with vigorous research programs has allowed us for the last 30 years or so to really address issues of Earth system science, understanding the Earth as a complex, integrated system. We know enough now to understand what our needs and requirements are, and we know enough to know that no single nation, no single agency can possibly solve the Earth system problem itself. And that leads to the necessity for cooperation and organization. And yet, what many of us think as collaborative space missions are not the only way in which cooperation could take place, and indeed in which cooperation and collaboration is taking place. And so most of the talk will actually be a survey from my point of view of various collaboration approaches and results that are taking place right now. And over all of that is the question from an international standpoint of governance. How does one herd the international cats, as it will? And I'll give you one example of interactions between the Committee on Earth Observing Satellites, GEO, in the area of forest carbon. So that's where we're going today. But let's start with some results and a bit of a conundrum. Long satellite time series of measurements of greenness, if you will, net primary productivity over land from 1982 to 1999 at the end of the last century showed that overall in a global mean, the net primary productivity of the globe over those 17 years was increasing, although clearly there are places where there's spatial variability. There's places where net primary productivity was decreasing, other places where it was increasing. But in the global mean, net primary productivity was increasing over that nearly 20-year period at the end of the last decade. Now, that kind of makes some sense. We know that the Earth is warming. We know that there's more carbon dioxide. Plants, more or less, at the level of understanding of a physical oceanographer, plants more or less on the land must like those conditions, and so productivity should increase. On the other hand, here we go. In the next 10 years, from 2000 to 2009, analyzing similar data sets from satellites, these are from MODIS, in fact, the net primary productivity of the globe averaged over the world actually decreased slightly over the last decade. The Earth is still warming. There's still more carbon dioxide. What exactly is going on? Being able to detect those results and to answer the questions of causality, the connections between processes, is key to what we do in Earth observations. And I'll tell you what the answer is here. The answer is, frankly, that the global decrease in net primary productivity is the result, as many people on this continent know, of a persistent and deep drought in the southern hemisphere. Oops. By the end of this talk, I'll learn to work this thing. So this brings me to what I consider to be, in English perhaps, the most profound four-word sentence that we can construct. And that sentence is, the climate is changing. The climate is changing, and it has profound implications. It's going to impact every aspect of life on our planet. We know from analysis of satellite measurements and in situ measurements that the globe is warming, not exactly uniformly, but just about everywhere the Earth is warming. The climate is changing, and we know that sea ice extents in the far northern regions of the Arctic are decreasing virtually inexorably year by year. In fact, just within the last couple of days, the sea ice, the minimum sea ice extent in September last month for 2011 is almost, not quite, but almost the lowest extent of sea ice that has ever been recorded. The satellite measurements allow us to quantify the sea ice extent to hitherto unforeseen levels of accuracy. And just as important, or maybe even more important than sea ice extent itself, the satellite measurements have shown that the composition of sea ice is changing. Red and warm colors on these plots indicate thick multi-year ice. Blue and cooler colors indicate, or green I should say, indicates thin single-year ice. What's happening is that the thick multi-year ice is modulated by ocean currents and temperatures, but thin single-year ice is modulated by solar insolation and clouds, a whole different controlling and constraining set of processes. The satellites have provided that information for us quantitatively. Our job is to understand why and how. There's less water in many mid-latitude and high-latitude land systems. Ice sheets, not uniformly, because indeed the center of Greenland, the ice sheet is increasing, but almost everywhere else, ice sheets on land are decreasing, and high-resolution measurements over many, many years from Landsat, for instance, show us on this continent that the glaciers of Mount Kilimanjaro, which some nearly 20 years ago were rather large, are now rather sparse. The climate is changing. And when you take water off the land, you put it into the ocean. And sea levels are rising virtually inexorably. And we know that in some detail. We know that in the global mean, sea level is rising 3.4 millimeters per year, plus or minus about 10% or so. We know that from the joint NASA-CNES precision radar altimeter measurements. And I'll be talking more about sea level rise in the ocean. And that sea level rise has profound implications for us here on the land itself. A huge fraction of the global population lives within a meter of sea level. In the city of Mombasa in Kenya, if sea level increases by 1 foot, 30 centimeters, about 17% of the city will be inundated, 4,600 hectares or so. And that's only a sea level rise of 1 foot. And remember, when we have more intense extreme events, such as typhoons and storms, the equivalent of that sea level rise happens more frequently, as you can see here. Okay, the climate is changing, and that poses profound societal challenges and responsibilities on us. As human beings, we are the only living creatures who actually can analyze and anticipate what the environment is going to be many generations from now, and we can act now to change our behaviors and possibly mitigate or at least change what's going to happen in the future. No other species on this earth has that possibility and has that ability. And so, for instance, one can, with some level of modest accuracy, calculate the relative change in the length of the growing period here on the African continent, and under various scenarios of carbon dioxide emissions, et cetera, we can predict what the growing period is going to be in the year 2050, say, compared to the present. And the situation looks relatively dire. In fact, for most of sub-Saharan Africa, the expectation is that the growing period is going to be somewhere between 5 and 20% less in 40 years than it is today. We have profound responsibilities because we can anticipate and because we do understand. From the joint NASA-German DLR, Gravity Recovery and Climate Experiment, GRACE mission, precision measurements of gravity can allow us to, can be interpreted in some areas in terms of the mass of water in aquifers. And you see that both in the Central Valley of California and in northwest India and Pakistan, a region here where 150 million people live, the aquifers are being drawn down by humans at an unsustainable rate. Something like 109 cubic kilometers of water were drawn out of this aquifer region over a period of just 6 months. And about a third of that was, 6 years, excuse me. And about a third of that was drawn out of the smaller region in Central California in a period of about 5.5 years. We can anticipate what's going to be happening in the future based on knowledge that we have about the Earth system and on measurements that we have, that we are making by the satellites. And finally, the fact that we know that the climate is changing is really, to my mind, a profound testament to our human skills and our intellect. Being able to detect the secular trends in the midst of a lot of high-frequency variability, being able to quantify things like 3 millimeter rises per year in global averages in sea level is really quite amazing. It should be amazing. It's amazing to me. It should be amazing to you. And we should feel very proud that we in the space community and the earth science community are bringing together the technology, the knowledge, and the interest in order to illuminate this problem, these problems and these effects, and understanding their causes for everyone. So I talked a little bit about the sea level rise from the joint TOPEX, Poseidon, and JASON missions, which are a collaboration between NASA and the French Space Agency, CNES. And we talked about the global average sea level rise. But in fact, if you look at the map of sea level rise, which is only possible because we're making measurements globally with the satellite systems, you see that there are some places actually where sea level has been falling over that period, and other places where sea level has been rising even more rapidly. In fact, if you actually pick various places, I'm not showing the chart here, over the time of the instrumented record from space, there are some regions where the sea level change is monotonic in time, up or down, but most other places there are periods of decades in which sea level increases followed by a decrease, or decreases followed by an increase, and there are some places where sea level is hardly changing at all. Furthermore, we can understand by putting together measurements from the altimeters, which are measuring sea level, if you will, directly, and gravity from the International Grace mission, we can understand why the sea level is increasing. Before I said, you take water off the land and you put it into the ocean, sea level is going to increase. But there's another reason that sea level can increase as well, and that's if you heat the ocean, it expands. And in fact, it expands, but its mass doesn't change. So measurements of mass through the gravity mission GRACE and measurements of sea level through the altimeter missions, TOPEX, Poseidon, and JASON, allow us to actually partition the sea level rise between steric effects, which is the heating, the expansion of the upper ocean, and the addition of water to the ocean. And if you will, somewhere between about a third and a half of the expansion is steric effects, and the rest is moving water from land to the ocean by melting ice sheets. By the way, sea level does not rise appreciably when you melt sea ice. Go home. Put an ice cube in a glass of water. When the ice cube melts, the glass doesn't overflow. Science lesson number 2. Okay. So, the Earth is a complex system. This is a simplification of the classic Bretherton Earth system diagram. There's physics and the physical climate system. There's biology and the biogeochemical cycles. There's external inputs from inside the Earth, putting particulates and chemicals into the atmosphere, say, through volcanoes, and changes in insulation from the sun. These are modulated by atmospheric dynamics and chemistry. The ocean is transporting about half the heat between the low latitudes and the high latitudes. The atmosphere is transporting the other heat. Human activities are changing the composition of the atmosphere, the state of the land, and a whole variety of other things. The Earth is an incredibly complex system. The key to understanding the Earth system is not simply characterizing individual processes, but rather understanding, in addition, the interaction between the processes. And in order to do that, one must be making measurements of many different variables, more or less at the same time, over the entire globe, because the nonlinearities in the system are linking all the scales. They're linking small spatial scales to large spatial scales. They're linking short time scales to long time scales. And frankly, only through the global view with high resolution, high accuracy, broad coverage, and frequent revisit that we get from the satellites can we acquire the measurements that are necessary to guide the science and eventually to run the models in the future. So the combination of satellites, which is telling us about various processes and how they interact, and our growing knowledge of the Earth as a complex system, is putting us on the cusp of being able to predict the evolution of the planet on which we live. However, as I said before, there is no single agency, and in fact, no single nation that frankly can expect to implement a standalone, spaceborne, Earth-observing system that can make all the measurements that are necessary in the ways in which they're necessary to be made. And therefore, collaboration is essential if we are to advance Earth system science and to deliver the full range of societal benefits. The extent to which we can harmonize and collaborate among all of the Earth-observing satellite nations and systems is actually going to help define and determine the quality of life of each and every person on this globe for generations to come. What I like to say inside NASA headquarters is that in the Earth sciences and Earth observations from space, we are not only doing something that's challenging and something that's interesting, we're doing something that's important. We have the ability in fairly direct ways and on fairly short time scales to influence life for each and every person on the globe. Therefore, we got to get it right. And how we do this collaboration is, as I said, almost as much an interaction or it's almost as much sociology as it is technology. So what I want to do now is actually go through a series, sort of a survey of various collaboration approaches, more or less one by one or two by two. When most of us think of collaborative space, Earth-observing space missions, we think about the so-called joint hardware contributions, in which multiple organizations, maybe multiple countries, contribute different parts of a particular spaceborne mission. One may have the launch vehicle, one may bring the spacecraft bus, an instrument from country A, an instrument from country B. You bolt them all together and you fly them. And indeed, that has been an approach, and it continues to be an approach that NASA and many other space agencies follow, and it has been very profitable. It is not necessarily either the easiest or the most direct approach, however, as we will see. But of our NASA 15 operating research missions right now, fully 10 of them, the ones with the solid circles on them, have significant hardware contributions from international partners. So this approach works. Our very latest launch, the Sakti Aquarius mission, is a classic example of joint hardware collaboration. Aquarius Sakti is a collaboration primarily between NASA, the U.S. Space Agency, and CONAI, the Argentine Space Agency, with a particular focus on measuring sea surface salinity, a key quantity both for oceanographers, because salinity affects density, and density drives a whole lot of ocean circulation, but also for hydrologers, because if you evaporate water from the surface of the Earth, you don't take the salt away, and it becomes saltier, and if you rain on the surface of the ocean, it becomes fresher. So sea surface salinity is not just an ocean quantity, it's actually a whole hydrologic cycle quantity. And Sakti Aquarius was, in fact, such an international collaboration to measure sea surface salinity and other things, primarily, as I said, between NASA and CONAI, but there are additional contributions from the Brazilian Space Agency, from IAC, the Italian Space Agency, from CNES, and from CSA Canada. Sakti Aquarius was launched on June 10th of this year, and I'm proud to say that, again, through collaboration of the science teams, the first science products were released, products on sea surface salinity were released within 90 days. And this is indeed the first light image. It's not absolutely fully calibrated yet. You can see various cross-swath biases and stuff like that. But under the circumstances, considering that it's a very subtle measurement to be making, the results are truly stunning. And you can go to the NASA Earth Science Data and Information System and get, on a routine basis right now, sea surface salinity from Aquarius Sakti. Let me just point out some of the features that Aquarius Sakti is showing right now. And by the way, the European Space Agency SMOS mission, Soil Moisture Ocean Salinity, is showing some of these features as well. They're well-known features like the high salinity regions in the mid-latitude gyres in the Atlantic Ocean and the somewhat more subdued high salinity regions in the mid-latitude gyres in the Pacific. But there are also, frankly, some unanticipated results here that, if they stand up through the calibration period, are going to be quite interesting. Look at the effect of the Amazon outflow and even the Mississippi outflow during a period in which there was some significant hurricanes in the Gulf of Mexico. These low salinity regions that are clearly connected to the river outflows are rather larger and of rather larger magnitude, larger in extent and magnitude than people had been thinking about. If you go back to that loop that we were showing at the very beginning while you were filing in, those of you who came in before the talk, you'll see that there's actually biological productivity increases associated with the large river outflows. Okay, so Aquarius Sakti is a classic example of an international collaborative mission. In NASA's plan of some 15 missions or so in the rest of this decade, or 13 missions in the rest of this decade, approximately 5 of them today have international collaborations in the classic fashion of instrument hardware collaborations built into them. But this is not the only way to do international collaboration in satellite missions. In fact, because the sampling issues are so great, we want to have global coverage but frequent revisit. One can also collaborate, and it's frankly a somewhat easier collaboration, by harmonization of co-orbiting missions. And there's 2 kinds of harmonization that I want to talk about. One kind is when multiple countries are flying similar sensors that make similar measurements. Well, you could fly them one right behind the other and get 2 measurements of the same thing almost simultaneously. That's great for people who want to calibrate 2 instruments, but it's not real great because both satellites are measuring at point A and no satellite is measuring on the other side of the world where things are changing. So harmonization of mission designs in terms of orbits could lead to increased sampling, increased efficiency, and frankly increased utility, and I'll talk to you about that. In the other example, different missions could be making measurements of different quantities. Then you might very well want to make those measurements at nearly the same time and the same place, and I'll show you some examples of the international A-train in which that's taking or is taking place and has been taking place. But let's talk about mission orbit harmonization first. We've talked a lot about sea surface elevation, long-term trends from the altimeters. Sorry, I'm an oceanographer. I like the ocean. It does happen to cover 75% more or less of the Earth's surface. If you're in a satellite, most of the time you're looking down at the ocean. The Jason nadir-looking satellites, a collaboration between the U.S. and France, have sampling characteristics over a week. These are the tracks of the measurements off the east coast the United States in the Western Atlantic that look a little bit like this. If one analyzes globally the sea surface elevations from JSON in a week, take a week snapshot, a 1 week, that is 2 E's, snapshot, and analyze sea surface elevation with homogeneous and uniform spatial variability, you see that the sea level is actually dominated by small scale ups and downs corresponding to mesoscale eddies. This was actually not widely appreciated until just the last several decades. That is, the influence that the small scale eddies have, or the variability that's tied up in small scale eddies, as opposed to the sort of larger scale currents like the Agulhas and the Gulf Stream and the Kuroshio, et cetera. But now let's combine the JSON altimeter measurements with other altimeter measurements that have harmonized orbits from the European Space Agency's ENVISAT mission. Same sort of measurements, virtually the same accuracy, a different orbit. And you can see that the orbital tracks fill in far more over that week. And in fact, when one analyzes the combined data set, one sees that in fact the quantity and scales of those eddies are both, well, the scales are smaller and the quantities are larger than we would have ever known, even from the single, from either of the single missions. This is powerful. And you can see that, in fact, the eddies tend to be concentrated in regions of strong western boundary currents like the Gulf Stream, the Kuroshio, the Agulhas, and the Antarctic Circumpolar Current, Brazil-Malvinas Current, et cetera. So only by combining the measurements from the European and the ESA and the NASA CNES missions do we get this appropriate, reasonably resolved global view. I talked, so again, that was harmonization of orbits. A different form of harmonization of orbits is making multiple measurements of multiple quantities at nearly the same time so that you get a temporal view, temporally resolved view of, say, atmospheric dynamics and chemistry from multiple missions. A view that one could never get by hanging any number of instruments on a single spacecraft, because the different instruments have potentially different viewing geometries. So the only way that you can make a limb sounding at this particular point and a nadir measurement at that particular point is to have the instruments separated on different platforms, but viewing the same area of the atmosphere at the same time. NASA and our international partners have pioneered the so-called A-train of constellations, a constellation of satellites for many years now. It's a wonderful international collaboration. It involves missions from several different countries, spacecraft that are flying in lockstep orbit, some of them very close to each other. Up until April or so of this year, the two missions, the French Calypso mission, French-US Calypso mission, and the CloudSat mission from NASA and the Canadian Space Agency, were actually flying within about 100 kilometers of each other. They were about 17.5 seconds apart, making complementary measurements of cloud structure and atmospheric composition from an aerosol point of view within virtually simultaneously. At the front and the back of the A-train were the large observatories of Aqua and Aura. And in the next few years, the A-train is going to be joined by the Japanese GCOM-W1 satellite and hopefully OCO2 as well. This is a remarkable feat, and frankly, this long-term constellation formation flying has been done with a minimum of management mischief and oversight, if you will. It's the working level groups themselves that have gotten together and have worked this out very, very well. And just to prove to you that it's not like the moon landing, which was cooked up in Hollywood by the U.S., this is an independent image that was taken in May of 2009 by an Australian amateur astronomer, photographer of both CloudSat and Calypso flying together in the A train. This is the star Vega. It's not moving. Both of the spacecraft are indeed moving, and you can see that Calypso has an active laser on it. It's a green laser, and you can actually see two of the laser shots in this 6-second exposure. These two instruments were and spacecraft were flying about 100 kilometers apart, 17.5 seconds apart. The data from the A-train, I mean, this is not just a mission operations thing. The data have actually are being used to great extent. Combining A-train measurements from CloudSat of precipitation and series measurements from the Aqua instrument of cloud albedo has been used to show quite definitively that precipitating clouds are brighter from above, more reflective than non-precipitating clouds. Cloud top pressure from the MODIS instrument on Aqua and the OMI instrument on Aura, the other of the big observatories, combined with CloudSat reflectivities, has given us new views of the composition of the particulates, the water particulates in clouds. Operationally, measurements from the multi-channel microwave radiometer, AMSR-E, on the Aqua spacecraft and CloudSat vertical profiles are used worldwide, and especially by the U.S. Meteorological Agency to better forecast precipitation patterns associated with severe tropical storms and hurricanes. It's with some regret that I report that just yesterday the antenna on AMSR-E, which is itself a JAXA-supplied instrument on a U.S. NASA spacecraft, that antenna, after many, many years, far beyond its design life, stopped spinning. We'll see whether our JAXA colleagues can get it going again. But when GCOM W1 launches into the A train in the first quarter or so of next calendar year, we will once again get Japanese multi-channel microwave radiometer data back in the A train. Okay, two other ways of collaborating are division of measurement responsibility, and I put it in quotes because we've never quite been able to establish that, and combining data from multiple missions for scientific and applications use. This is sort of the collaborative analysis of non-harmonized measurements. The division of measurement responsibility is an interesting one to think about, though. Imagine if we could decide that the European Space Agency would concentrate on atmospheric chemistry measurements, and NASA would concentrate on several other kinds of measurements, perhaps of ocean dynamics, and SANSA would concentrate on a particular measurement of atmospheric dynamics or terrestrial productivity or something like that. And we agreed among ourselves to push the technologies in our areas far forward and to exchange all data, harmonizing the orbits. Imagine it would be nirvana for the research community. But so far, we haven't been able to do that. Okay? On the other hand, we have, by making the data available from our multiple missions, we have allowed the research community to combine the data for scientific and operational use. A key example of that is going to be when it launches in late 2013 or early 2014, the joint NASA-JAXA Global Precipitation Mission, in which we will, for the first time, be combining measurements from a whole wide variety of instruments and missions from many different countries, Megatropique from France and India, for instance, the GCOM series from JAXA, a whole wide range of measurements in order to get, for the first time, global accurate precipitation maps on a 6-hourly basis. GPM itself is a hardware collaboration between JAXA and NASA, in which JAXA is supplying some of the instruments on the core spacecraft, NASA is supplying others. NASA is supplying the spacecraft, JAXA is supplying the launch, and we're going to use the core spacecraft to characterize all of these other instruments and missions, many of which were launched by other agencies and other countries for different reasons, but all of which, once characterized, can actually contribute to accurate global precipitation measurements. Very recently, within the last month or so, a signal paper has been published by Eric Rignot and colleagues regarding providing for the first time accurate measurements of surface ice velocities over the entire Antarctic landmass. The way in which this was put together was not using measurements from any single satellite, but rather using interferometric SAR measurements from LOS PALSAR from Japan, ERS-1 and 2, and ENVISAT from Europe, and RADARSAT-2 from Canada. By having all of those measurements available to the scientific researchers, they can pool them and develop better insights than one could get from any individual mission alone. And some of their insights are truly astounding. I didn't include their movie in here, but their maximum velocities in some areas are for ice sheets are quite large, approaching a kilometer a year in some areas, and over 250 meters a year. That's like a meter a day in many other areas. This, by the way, is an interesting interaction potentially between sea ice and land ice, because if you melt the sea ice that was acting as the cork in the bottle for the outlet glaciers, then it turns out that the glaciers drain into the sea far more rapidly than we had thought. This has profound implications in our modeling of sea level rise. And finally, there's collaborations that don't even involve entirely spaceborne measurements. NASA and the European Space Agency are, as an example, working very hard right now under formal framework agreements to provide joint calibration and validation for our similar missions sometimes and for field campaigns. And we are collaborating in our ground systems, including mirroring large data holdings of the other. An example of the calibration validation is NASA's IceBridge and Cryosat-2 calibration. We have been flying aircraft measurements since the demise of the NASA ICESat-1 satellite, which measures precision ice topography over the land. We've been flying aircraft measurements over key IceSat lines in order to preserve that time series until we launch IceSat-2 in the 2016 time frame or so. It turned out, however, that by collaborating with the Europeans, with ESA, soon after the launch, very soon after the launch and turn on of Cryosat, that we had IceBridge flights that were out at the same time that they were turning on Cryosat, and so we adjusted our flights to underfly Cryosat and provide the first direct calibrations, and that has continued between NASA and ESA over the subsequent Antarctic and Arctic campaigns of Icebridge. We would have flown Icebridge anyway for the climate continuity aspects, but by making the data broadly available and by communicating between the agencies, we get so much more scientifically for the investment by being able to underfly at the precise time that they're coming over us cryosat-2 lines. Okay, and this brings me to the sort of international governance approach. There are, and have been for many years now, several organizations which are designed, in part at least, to help to achieve these coordinations and harmonizations. It started way back when, in '72 perhaps, with CGMS, which was focused on meteorological satellites, operational meteorological satellites. In '84, the Committee on Earth Observing Satellites, CEOS, got started. There were several other international groups that are listed here. And in 2003, of course, the Group on Earth Observations, the International GEO, became a key player in the international coordination and Earth system identification game. So let me talk a little bit about CEOS. It was established in '84, as I said, under what was then the G7 Summit of Industrial Nations. And the idea was, in fact, for CEOS to be an organization which focused on coordination of space-related Earth-observing activities to optimize the benefits through cooperation. It's a strictly voluntary organization. Best efforts of members and associates. We have 29 space agencies as members, all the ones that you would think of and many that you don't. SANSA is a full member, the South African National Space Agency that's new, and we have 21 associates, UN agencies, different programs supporting ground facilities. And CEOS is the space coordination arm for the GEO system of systems and for GEO. Our overarching objectives in CEOS are indeed to optimize the benefits through cooperative mission planning. I talked about that. Compatible data products, formats, etc. I talked about that. And importantly, through education and capacity building so that the space agencies and the research communities are not simply making available data and information, but rather we're preparing all of the countries or many of the willing countries in the world through building their capacity to utilize that information in effective ways. CEOS serves as a focal point for much of the international coordination in Earth observing activities, and we also attempt to harmonize policy and technical information to encourage complementarity. An example, and it's the only example that I'll show, it's 3 or 4 slides long, of a major initiative which is going on right now, the GEO Forest Carbon Tracking Initiative and the Global Forest Observation Initiative is an example in which this sort of governance is helping to provide information for everyone around the globe in important policy-relevant areas. About 17% of the global greenhouse gas emissions can be traced to land use changes, in particular deforestation. So in order to understand the mechanisms and to track the efficacy of policies that are associated with international agreements that we might want to engage in, we need to monitor global forest carbon stocks and emissions. We need to do it comprehensively, we need to do it continuously, and we need to do it systematically for MRV, monitoring, reporting, and verification systems, etc. And GEO established the FCT CASC in 2008, and we are hoping, or people are hoping, that will indeed become a larger, more global forest observation initiative into the future. But the key is, how do we put together the satellite measurements that are being acquired from multiple instruments flown on missions by multiple countries, the in situ measurements and protocols that are being done, that are being carried out on the ground, in order to provide everyone with a uniform, consistent, tied to standards view of the evolution of forests around the world. So the GEO-FCT task is, in fact, to provide a framework for coordination, to identify key areas, national demonstrators that show the elements of what we hope will eventually be a global system, and to establish the institutional arrangements for data access and continuity. In terms of the national demonstrators, in 2010, we had identified the following sites that are in red as national demonstrator areas. In situ measurements were being made there. Wall-to-wall satellite measurements were being requested from all the relevant space agencies, and processes and standards were being established. In 2011, the demonstrator area expanded. In 2012, again, and by 2013, we hope to have coverage of about a quarter of the global land and about half of the forest areas in the world being measured wall-to-wall by satellites under standard protocols. An example of the sorts of products that can be calculated from such a set of sites and utilizing the measurements from multiple satellites is this map here in Africa of forest change in Cameroon. And you can actually see that forest change here is not all one way. Yellow is non-forest to forest. Purple is forest to non-forest over this period of about 24 years, a quarter century or so. And you can see that there are regions that became reforested, and there are key regions that became deforested. This is important to know, because if one only focuses on the evolution of presently forested regions into the future, you have what turns out to be the so-called leakage effect. Sure, you may take forested or deforested regions today and change their state, but that doesn't necessarily tell the whole story about the carbon emissions even from that nation or from that region, if in fact there are other regions that are changing in the opposite direction, maybe even larger. And so this initiative involves putting together measurements from a whole variety of optical satellites, from the US, Landsat, from India, from before 2010, China and Brazil, high-resolution measurements from SPOT, and synthetic aperture radar measurements at L-band, C-band, and X-band from a variety of different agencies, nations, and missions. Coordinating these data acquisitions over the demonstrator areas in order to ensure wall-to-wall coverage over the time period, and rather remarkably, frankly to me, through the coordination efforts of CIAS and the umbrella of GEO, we have been, frankly, remarkably successful. There have been more than 116,000 scenes over the demonstrator sites that have been specially acquired just since the summer of 2009 into the spring of this year. Provision of satellite data is obviously key to extending this to the Global Forest Observation Initiative. We must have mission continuity in order to build the large, long time series that are necessary. Right now, Landsat is the longest continually acquired and consistently processed global satellite set of measurements, and it's only about 35 years long, and it's only continuous because some of those missions have lasted an unbelievably long time. At present, as I mentioned, like for AMSR-E, instrument failures are reducing the supply of data from the satellites. CBER's failure in spring of 2010 is an example of that. And if we are to have the national monitoring, reporting, and verification programs using satellite data, we have got to provide them with some assurance that they're going to get sustained inputs. So in conclusion, let me end this tour of satellite measurements and international collaborative approaches with this summary. The satellites provide global data. They have high spatial resolution, frequent sampling, global coverage, and satellites can be used to make many different measurements of many different variables. And that's what you need in order to advance Earth system science and derive from that societal benefit. It's too big a job for any one organization or any one country to make all the measurements that are necessary, and international collaboration is absolutely essential. We're not putting all our eggs in one international collaborative approach. Many different approaches are being utilized to good effect, and they're providing, frankly, mutual benefit to everybody that is involved. But key to all of the approaches is free and open data exchange. That's the only way that the research communities and the applications communities will be able to maximize the benefits from the partially harmonized, if you will, satellite missions that our individual nations are flying. And finally, if you only remember one thing from this, success is not optional, it's necessary. Our spaceborne Earth observations can, and indeed they are, providing real societal benefits from disaster relief to environmental forecasting. Our countries, our people actually are beginning to understand that. Our leaders and our legislators are beginning to understand that. And they're starting to expect those benefits and increases in those benefits from us. It's incumbent on us to not only solve the technological problems and not only solve the scientific research challenges, but to solve the coordination governance issues that are keeping us from maximizing the benefits. When we do that, we're going to have support across the board. So thanks very much.
Thank you. Thank you, Mike. That was terrific. What we'd like to do is take some questions from the audience now. Deb Vane is volunteered to distribute the microphone. Do we have a question out there? Graham, up here.
Dr. Gibbs.
Would you use the mic, please?
Mike, first of all, I'm going to say thank you. That was probably the best highlight I've ever heard.
Well, thank you.
But that's not my question.
He wants you to say that into the microphone.
That wasn't a question.
Record it up there.
People are leaving in droves after that gone.
Many space agencies are scientific organizations. I think you probably know what's coming. Could you talk about the issue of research to operations and how we can handle that globally?
No, I'm not going to talk about. The question is, can I talk about the issue of research to operations? And the answer is no. I have no intention of talking about research to operations, but I'll talk about something similar. We saw that we need to make measurements of many different variables. We need to make them globally, and we need to make them over long periods of time to extract the trends from the high-frequency variability, to resolve the real important time processes that exist, many of which are driven by the ocean that has very long time scales. So the issue is, should the same agencies that are developing the measurement techniques be saddled with, that's pejorative, be saddled with making the measurements that they have pioneered over the time scale that's necessary to advance the science. Okay. Now, operational agencies, the agencies that make measurements for forecasts on a regular basis, products that are clearly defined and are produced to some level of standards on a regular basis. Operational agencies like NOAA, KNMI, ECMWF, et cetera, typically focused on short-term weather forecasts, but not exclusively, tend to make measurements for long periods of time. We got to make these measurements for long periods of time for two reasons. One of them is we have to predict tomorrow's weather forever. Not that we have to predict the weather a long time from now forever, but we're always going to have to predict tomorrow's weather. So we have to have a system in place to make measurements for long periods of time to feed the short time scale forecast. We also need to make the measurements for long periods of time, as I talked about, for Earth system science reasons. The question that Graham brings up is, how do or should we use the short-term forecasting data acquisition systems to also be making the long-term measurements of many different quantities? And it's not clear what the answer is to that. The infrastructure is in place to support short-term meteorological forecasting, but it's not obvious that all of the necessary infrastructure, data processing, and decision approaches exist. Right now, NASA and NOAA are engaged in the long-term dialogue, let's put it that way, of harmonizing our NASA research and development approaches with NOAA's mandate for making long-term measurements. This is happening all over the world as well, with ESA and EUMETSAT and elsewhere. It's a real conundrum. It is not at all obvious that the answer is that the research agencies should develop and prove a technique and then throw it over the transom to be picked up by another agency whose focus is on some sort of prediction process, but who has in place a long-term data acquisition scheme. This has got to be worked out probably on a measurement-by-measurement basis. That's the long answer to your short question. The long non-answer.
Great presentation. I'm Madhut Khan, Center for System Studies in NASA Marshall Space Flight Center. My question is, when you talk about collaboration, there's also an element of competition in this, and how is that managed or that can be managed? My second question is, do you at NASA have a playbook in which you say that these are the missions which NASA would invest itself because of national interests, and these are the ones that we would look for partners and collaborators? Thank you.
Okay, I'll answer the second part first. The question for those who may not have heard is, does NASA have a plan of the strategic missions that we intend to fly with an idea of international collaboration from the standpoint of hardware collaboration, I assume you meant. And the answer there is absolutely yes. I showed you that sort of waterfall diagram before of the NASA missions. It's guided by the National Research Council's decadal survey, modulated by administration and national priorities having to do with getting measurements for policy decisions, not necessarily for research, et cetera. So we have that plan. It's called the NASA Climate Initiative. It's been endorsed by OMB, Office of Science and Technology Policy, and all of the U.S. Global Change Research Program, 13 agencies. It's on the web. Yes, we have it, and we have a good idea of the international collaborations in the classic sense that we're moving to. In that plan, we have, to a certain extent, ceded to other nations and other organizations some other measurements, because we don't even have enough resources to cover all the measurements that the NRC, the Research Council, said that we should be making in the decadal survey. So the decision, among the decision criteria that we used in putting together our plan was who might be making measurements that we would have access to so we don't have to duplicate them. And that leads to the competition portion of your statement. I'm not sure whether there's actual competition or whether it's mutual recognition of what the real important measurements to be made are. I am certainly sure that there is no need for destructive competition. The sampling issues that we talked about before, remember with the altimeters, et cetera, are so large that even if two nations in general wish to fly the same type of measurement mission, if we coordinate and harmonize the orbits, there will be no competition and strong mutual benefit from both of those. So I think that it's rather short-sighted and superficial to view the situation as competition. Remember, we've got to be making these measurements for a long period of time as well. A year of new measurements of a new type, say European Space Agency or SANSA or JAXA or IAC, gets an instrument out a year before NASA does. In the cosmic scheme of things, that's very worthy, but it's not exactly going to get you a Nobel Prize.
Okay, we're starting to run short on time, so I'm going to take one more question.
This is, by the way, the Nobel Prize season, so get your votes in for next year.
Yeah, I'm Afaq Raza Khan from India, and I was a participant of the UNIF workshop, and there we discussed in a part the importance of open database systems from space organizations, so that you don't need ISRO to build another spacecraft to collect the same data that NASA already has, or vice versa. So what do you see? Is there a future for space organization to have open database systems or open data sharing?
As I said in the talk, the question is, if I get it correctly, what's the role of open data acquisition and open
and
data
free
sharing?
data acquisition for the future? Like
Right
now you have barter system, you give some data and you get some data, but in the future maybe an open data.
Okay, good point. As I said in the talk several times, it's absolutely necessary to have free and open exchange for everybody, whether they bring data to the table or they don't bring data to the table. We must make all of the measurements that we are acquiring available with their appropriate metadata to everybody. That's the way that all the smart people around the world are going to be able to contribute through research, through applications, to greater understanding and societal benefit. I'm proud to say that NASA has virtually from its inception, certainly over the last 25 years or so, in the area of Earth observation, we have a completely free and open data policy for our NASA civil Earth observations. The data are available with no period of exclusivity to anybody that wants it. I am firmly of the belief that that is essential if we're going to pull off advancing in Earth system science. Now, the issue that you raised of what if another country, how do we assure continuity is basically what you're saying if a particular country doesn't commit to continuity from the start. That is a very difficult governance issue. I'm proud to say that in the arena of the US, NASA, and ISRO, in the area of scatterometry, the measurement of surface vector winds, wind speed and direction over the ocean, NASA flew the QuickSat scatterometer mission from 1999 to 2009, I guess. And the Indian Space Research Organization is presently flying a nearly identical instrument that they launched 2 years ago, I guess just 2 years ago, and we are cross-calibrating those two instruments. There was a short period of overlap before QuickSat died, but QuickSat is actually still making backscatter measurements. We've moved QuickSat so that it's making its measurements at the exact same geometry that the ISRO OSCAT instrument is making measurements. And so we're actually having a multi-decadal calibrated data set of backscatter cross-sections. So this can be done. It can be done without presidential, ministerial level decisions, and it helps out all humanity. What we can't do is everybody get together and assign to some third party, maybe who wasn't at the meeting, that they need to fly some mission because the rest of us aren't going to. That doesn't work.
Okay. Thank you, Mike. We appreciate that. I would point out that we have on the stage up here some documentation describing CEOS. If you're interested, Mike had discussed it, and so if you would, if you're interested, please pick up a page before you leave. Mike will stay around for a couple of minutes and answer some additional questions. But we want to thank all of you for delaying your dinner and coming here tonight and listening to what he had to say. We all really appreciate you attending the session. Thank you.